Our lesson today not particularly difficult, but there's a lot of information because we talked about triple integrals and applications all in one lesson. Where with double integrals we'd split them up. So I want to get started. So what we're going to do today is use a similar procedure that we did to what we did to define a double integral. And we're going to come up with a definition of a triple integral, and then we're going to talk about some interpretations, some applications of triple integrals. So what we're starting with is we have f of x, y, z, and this is going to be continuous. So it's a nice function over a bounded solid region Q. So we're using Q instead of R because we're talking about a solid region rather than a plane region. All right, so visually what we have, there's our first octant, and we have some solid that cuts into the first octant here, and this, so we have some f of x, y, z above the xy plane. We're visualizing this as a solid region, and what we want to do is divide Q into small rectangular prisms. So I'm going to have a little rectangular prism here, like so. There's our small rectangular prism. And we're going to say that the volume is delta V sub I. And delta V sub I is going to be, this side of the rectangular prism is delta Y sub I. This side would be delta X sub I. And this would be delta Z sub I. So delta V sub I is we're going to multiply base times width times height, X sub I, Y sub I, Z sub I. And we're going to say that X sub I, Y sub I, Z sub I is a point inside the prism. And then we're going to find the volume, the total volume. Is going to be approximately the sum, I equals 1 to n, of f of x sub I, y sub I. No, this is not going to be a total volume. So we're going to form this sum. Y sub I, z sub I, times delta v sub I. And f of x, this f function could be various things. It could be a density. It could be a charge per unit volume. It could be some other quantity in that volume. So we're multiplying some function times the volume there. And we're going to take the limit as delta v sub I approaches 0. So again, f of x, y, z could be a density, mass per unit volume, could be a charge per unit volume, just some quantity defined over that region Q. So we're going to take this limit as delta v sub I approaches 0, and that's going to be our definition of a triple integral. So we're setting this up exactly the same as we did to define a double integral. So we're going to define a triple integral and we're going to have triple integral over our solid region Q of f of x, y, z dv, and that's going to be this limit as delta v approaches 0. And again, what we're saying with this delta v approaching 0, we're saying the longest diagonal of the prisms that we divide our solid into, the longest diagonal approaches 0. The sum I equals 1 to n of f of x sub I, y sub I, z sub I, delta v sub I. So that's going to be our definition of a triple integral. The volume of the region Q, volume of Q, is V, would just be the triple integral over our region of delta V of dV. So we're just summing the volume of all those little rectangular prisms. Triple integrals have properties that are very similar to properties of single integrals, properties of double integrals, and I'm not going to list them all, but we can look at our properties on page 1009. So the properties, we can sum triple integrals, we can multiply by a constant, all those kinds of things that we're used to being able to do with integrals, we can do with triple integrals as well. If we have a nice region, if our Q is a nice region that can be divided into rectangular prisms easily, we evaluate these exactly like we did double integrals. We evaluate them as a triple integral. So we'll say for nice solids Q, we evaluate like double integrals. And in that case, dV is any permutation of dV equals dz dy dx. So there are 6 possible orders of integration for a triple integral. Any permutation of these 3. We usually, we're going to set up our dV as dz dy dx, or dV equals dz dx dy. So we're usually thinking of our surface being above the xy plane. So we have a surface, z equals f of xy, and then the dy dx, or the dx dy, is then our double integral in the xy plane, just like we've been doing. So for example, if 0 is less, or a less than x, less than or equal to x, less than or equal to b, h1 of x less than or equal to y, less than or equal to h2 of x. So we're dividing our region in the xy plane into vertical rectangles. And then we have a surface up above the xy plane, g1 of xy less than or equal to z, less than or equal to g2 of xy. Then our triple integral over our region. of f of xyz dv is going to be the integral. X is going to go from a to b, y is going to go from h1 of x to h2 of x, and z is going to go from g1 of xy to g2 of xy, and this would be f of xy z dz dy dx. And each integral is each iterated integral, just like we did with double integrals, we evaluate by letting the other two variables be constant, or considering the other two variables as constant. So we're just adding one step. And this setup, usually we're visualizing a surface above the xy plane, and then this second pair of integrals, the dy dx, that's our double integral in the xy plane. So once we evaluate the first one, then we just have a double integral, and our region is the region in the xy plane. All right, questions so far? Okay, I want to set a couple of these up, and then we'll talk about some applications of triple integrals. So what we can do now is we can find, one of the applications is we can find the center of mass of a solid. So before we've been finding centers of masses of planar lamina, so thin sheets of material. Now we can find the center of mass of a solid. Find the moment of inertia of a solid about an axis or about a point. So that's going to be a couple of our applications. All right, so this first one, just an evaluation. Integral from 0 to 1. Integral from 0 to x. Integral from 0 to x, y of x dz dy dx. We could interpret this as we're integrating the function x that's below the surface z equals xy, and bounded in the xy plane by y equals x from x equals 0 to 1. And x would be maybe a mass per unit volume, a charge per unit volume, something. So let's evaluate this. Our first integral, we're holding x and y constant, and we're evaluating with respect to z. So we get xz, and z goes from 0 to xy, dy dx. So that, when we evaluate that on our limits, 0 to 1, 0 to x, we get x squared y dy dx. And now we just have a iterated integral in the xy plane. And we evaluate this. This is an easy evaluation. You can keep going, and we get 1/10. All right, questions there? So really, what we're doing here, we're just adding one more integral to what we've already done. One more integral, one more variable. We could continue the process. You could have quadruple integrals, quintuple integrals. You can do as many as you want. The process is the same, as long as your functions are nice. Just want to add up more stuff. All right. That's basically human history. How do we add stuff up? Find the volume of the solid. Bounded by, the other nice thing about triple integrals is it gives us a nice reason to draw interesting solids. Bounded by z equals 9 minus x squared, z equals 0, y equals 0, and y equals 2x. So this is a region, z equals 0, y equals 0, and y equals 2x. That's defining a region in the xy plane. So what we're talking about is a volume beneath this solid, bounded by this region. So this is our surface. So beneath this surface, this is defining a region in the xy plane. All right, so what is this surface? Z equals 9 minus x squared. Let's draw a picture. So in the xz plane, we get a parabola, and we're bounded by y equals 0. So we start here. Well, y can be anything, right? Yeah? So we go, it's a parabolic cylinder. Yeah, like a tunnel. And we're bounded below by z equals 0. And this y equals 2x. That's a plane. So let me erase this back here because I'm going to draw my plane. That line in the xy plane is y equals 2x. So the solid is in here. This is our solid cube. So that little wedge of that parabolic cylinder. So in the xy plane, if we turn this, we get the line y equals 2x. And what is this? This point where they intersect. X equals 3. That's when z equals 0. X equals 3. All right, so this is our region in the xy plane. So I would divide this into vertical rectangles in the xy plane for the two iterated integrals in the xy plane. So our volume is going to be the integral from x equals 0 to 3, integral y equals 0 to 2x, the integral z equals 0 to 9 minus x squared, dz, dy, dx. Mm-hmm.
I still don't understand the first one, like how you got that, like the wedge.
Y minus 2x. That's in the xy plane, we get that line. But z can be anything. So it goes vertically. So that plane is slicing into this thing right along the z-axis there. What do we get after we evaluate this once? Evaluate that first integral. Right, we get 0 to 3, 0 to 2x, 9 minus x squared, dy dx. Isn't that what we would have gotten if we would have found the volume of that, the volume below the surface? Z equals 9 minus x squared, bounded by this region in the xy plane. Yeah. So this is exactly like what we did with double integrals, finding an area. After we evaluate the first integral, we get something that is familiar. Now what we're going to do when we start talking about applications is we're going to put stuff in here and interpret that in various ways.
Is there just an answer for this?
I did not evaluate this one. It's easy to evaluate though. All right, let's look at one more where we switch the order of integration. All right, we want to sketch the region. And then switch the order to dy, dx, dz.
So why would you want it in that order?
What's that?
Why would you want it in that order?
Just because. To help us work on our visualization skills of three-dimensional solids. All right, so z, from the limits, z goes from 0 to 12 minus 3x minus 6y over 4. What is that? So between z goes from between z equals 0 to z equals 12 minus 3x minus 6y over 4. That's a plane. How do we sketch that? Yeah, we plug in some zeros and get a region in the first octant, at least, right? So if x and y are 0, z equals 3. So we get a z equals 3 there. If x and z are 0, y equals
12.
what is it?
Sean doesn't know.
Y equals 2 when x and z are 0.
Right.
And when y and z are 0, x equals 4. So in the first octant, that surface is that piece of the plane. All right, so we want to switch the order to dy, dx, dz. So what we're visualizing here is the surface is above, we're thinking y as the height. So the surface is above the xz plane. So our solid is going from the xz plane up to the surface, and then our region in the plane is going to be in the xz plane. So this triangular region is the base. We're thinking of that as the base of our solid, and the solid goes from that plane up to the surface. So what is the equation of this line in the xz plane? Y equals 0, right?
Yeah.
In the xz plane, y equals 0. So substitute y equals 0 in there, and we get, rearrange a little bit, and we get x equals 12 minus 4z over 3. And in terms of x and z, we could call this surface, if we solve this equation for y equals 12 minus 3x minus 6z over 6. That could be the equation of that surface in terms of its height above the xz plane. Is it 4z? Yes, it is. All right, so when we switch our order, now this is our region in the xz plane. So we have the inner integral is going to be y equals 0 to 12 minus 3x minus 4z over 6. That's dy. We want x to go from 0 to 12 minus 4z over 3. And z is going to go from 0 to 3. That would be our integral with the order switched. We won't have to switch, really, for triple integrals. For the most part, you might switch the order in the xy plane. Usually we visualize the surface being above the xy plane. Yes?
So hang on, the part that's x equals, is that like line piece or the projection, that triangular section?
So our region in the xz plane is here, so we're making vertical rectangles
Okay, so
here.
it's the triangular piece.
Yeah.
It's not the slanted part, it's the projection of this, if you imagine this as a pyramid, it's the projection of that pyramid into the xz plane.
Well, it's the intersection of that
Okay.
pyramid in the xz plane.
Okay.
All right, questions there?
How do we get that? Did you just solve it for x? Like,
Yeah, it just substituted y equals 0
Okay.
and solve for x.
Okay.
Because in the xz plane, y equals 0.
Cool.
All right, I have some additional examples on a video. So I'll write that up, but we're going to talk about our applications next. Additional examples are on a video called Calc 3 2013 14.6 additional examples. And I think there are a couple more that I set up on there. Now, sometimes it makes sense with triple integrals to evaluate the z integral first, and then maybe your integral in the xy plane, the iterated integral that you have in the xy plane, would be easier in polar coordinates. So then you can switch to polar coordinates in the xy plane. And that's essentially what we do when we talk about cylindrical coordinates. All right, let's talk about applications. Our applications are just a straightforward analog to what we talked about with double integrals. We can find our centers of mass and moments of inertia. I remember in my introductory physics class in college when we talked about moments of inertia, and parts of the homework were finding moments of inertia of various solids by doing this stuff. So here we're going to say that rho of x, y, z is mass per unit volume. So for planar lamina, we said rho of x, y is mass per unit area. And using triple integrals, our mass of a solid region is going to be the triple integral over our solid region of rho dv. So there's one interpretation of the function that can go in your triple integral. It could be a density function. M sub yz is a triple integral over a region. M sub yz is the mass times its distance from the YZ plane. So that's going to be x rho dv. And this is the moment about the YZ plane. M sub xz is our mass times its distance from the xz plane, q, and the distance from the xz plane is y rho dv. And the moment about the xy plane is the mass times its distance from the xy plane. That's going to be z rho dv. And remember, a moment is just the mass times its distance from something. Here we're talking about the distance from the plane. And our center of mass now of the solid region, x bar, is going to be m sub yz over the mass. Oops. Y bar is going to be m sub xz over the mass. And z bar is going to be m sub xy over the mass. So we can find the center of mass now of some solid region. And that's useful, finding the center of mass, because an object moves as if all of its mass were concentrated at the center of mass. So you can simplify your calculations by doing your equations of motion in terms of the center of mass and not have to worry about the whole solid thing. So we can find the center of mass of a solid region. We can also find our moments of inertia. We can find the moment of inertia of a solid rotating about an axis, just like we did before. So our second moments which give us our moments of inertia. We're just multiplying our mass times the square of its distance from an axis. So I sub x is the triple integral over q over our region. Distance from the x-axis, y squared plus z squared rho dv. I sub y, just our distance from the y-axis. Same triple integral. Distance from the y-axis is x squared plus z squared rho dv. I sub z, about the z-axis, x squared plus y squared rho dv. We can do a couple of things to shortcut some of these calculations. Some of these calculations can turn out kind of difficult, especially in rectangular coordinates. We can define our moments of inertia about a plane. So I sub xy is the second moment about the xy plane. Well, the square of the distance from the xy plane is z squared rho dv. And I'm going to do these sideways. This is about the xy plane. I sub yz, square of the distance from the yz plane. So that's x squared rho dv. and I sub, which one am I, xz? Y squared rho dv, and this is about the xz plane. And then we can find our moments about the axes by adding these together. Sometimes these integrals are easier to evaluate, just a z squared or x squared or a y squared instead of both. And we can say I sub x is I sub xy plus I sub xz. I sub y is I sub xy plus I sub yz. And I sub z is I sub xz plus I sub yz. Sometimes using this can save a lot of effort because often these integrals are easier to evaluate than these integrals. All right, questions? So again, what we're doing here is setting up and evaluating iterated integrals. The setup is exactly the same as the examples we already did. We're just putting something in here, interpreting that quantity differently than we did before. All right, I have some pictures that I want to show you, and I want us to interpret some things about the center of mass and moment of inertia, and then I have one last question for you. So let me find my pictures. I forgot to open those earlier. Chapter 14. All right. So let me grab this. So what we have here, we have a solid region, and I'm going to say for this region, the density is constant. And this is the center of mass, 208/5. That's the density of that, or that's the center of mass of that region with constant density. So we have this parabolic cylinder. This is similar to the shape we drew before, except it's along the x-axis instead of along the y-axis. And we want to know how the center of mass would change if the density were rho equals kx. So how does the center of mass change? What did you say, Sam? Yeah, we're gonna have more mass as x increases. So our center of mass is going to be, it's the y and the z coordinates aren't going to change. The y is still going to be 0, the z is still going to be 8/5. But we're going to shift further along the x-axis. How about 44? If rho is kz, it's going to shift up, right? We have more mass higher up. The higher up we go. So we'll shift up. I'm going to say positive z. How about 45? If our density is ky plus 2. How's it going to shift? To positive y. It's going to shift. So it shifts this way. So it wouldn't be right there on the x-axis anymore. How about 46? If rho is kxz squared y plus 2 squared.
Yes.
It's going to be positive everything, but z is more positive, and y even more positive. So we're going to have more mass concentrated higher up and further to the right. More for y and z. All right, we good there? All right, let me grab another picture. All right, so this time we have two solids, and they have equal weight, and they're rotating about this axis. For A, which one is going to have the greater density? B, right? We have more same mass, less volume. So that would be solid B. Which one is going to have the greatest moment of inertia? So the moment of inertia, remember, is the mass multiplied by its distance from the axis of revolution squared. B, it has more mass further away from the axis. And C, the solids are rolled down an inclined plane. They start at the same time and at the same height. Which one is going to get to the bottom first? A, because it has a lower moment of inertia. Remember, the inertia is the tendency of a quantity to resist rotation. All right, questions there? All right, I have this next one. We're not going to go all the way through the solution method. I just want to talk about how we would set this one up. You'll see one like this next one in your homework. So here is our setup. That point is at 0, 0, 4. This point is at 0, 3, 0. And this point is at 5, 0, 0. And we're going to say this is a solid region. So there's our solid region. And we're going to say that rho, our density, is a constant. Well, all we have here is the intersection of that plane with the axes. What do we need to set up and evaluate our triple integral to find the center of mass? We need some kind of equation. We need an equation of the surface, right? We can come up with an equation of this line in the xy plane. That's pretty easy. But we need equation of the surface. We need f of x, y, z. To set up our triple integral. Well, how are we going to do that? We need a normal vector. Well, how are we going to make a normal vector? Set up two vectors. So I'm going to I'll turn this segment into a vector. I'll call that P. I'll turn this segment into a vector. I'll call that Q. And a normal vector is P cross Q. So we can find a normal vector to the plane. And I'm going to say, let's say that gives us the vector ABC. And then the equation of the plane is A times, I'll use x minus 5 plus B times y minus 0 plus C times z minus 0 equals 0. So I'm going to say this is our point on the plane. And now we have the equation of our surface, and we can set up our triple integral. So if we have some information about a plane, we can always come up with an equation of the plane by finding our normal vector. So that stuff with normal vectors and equations of planes and all that stuff doesn't go away. In chapter 15, which comes soon, all of that stuff comes back very strongly. Gradient, normal vectors, tangent lines, all that stuff. We mix it up with double and triple integrals. Big part of a couple of the big theorems in chapter 15 relate triple integrals of a certain quantity to double integrals of a different quantity, relate double integrals of a certain quantity to a single integral of another quantity. So we get all kinds of interesting relationships between single, double, and triple integrals. We'll talk about how we can find a single integral, use a single integral to find the area of a region. Yes, Mr. Leader?
Are you giving the CML that I have?
Is it this week?
Yeah. You want to give it to me?
They like it to the quiz.
Yeah. You could do Wednesday or Friday, whatever.
I'll have to take a look. Yeah.
Okay.
Okay. I didn't think the CML was this week.
Jacob Pelkey. Oh, there's Jacob Pelkey. There he is. Always says coming out and seeing Jacob Pelkey.
Oh yeah. I have in my notes. I have CML tutor time. All right.
Coming from math?
Yeah. Imagine that.